Hello, everyone. So today I want to talk about something that is encountered quite commonly in any type of scientific or engineering calculation. So it has to do with the idea of a table. Very often we use what are called lookup tables for our calculations. For example, you may say, well, I need viscosity as a function of temperature. So instead of using a formula to do that, which may or may not be readily available, you may have some data, viscosity versus temperature, and you want to use that data from a table. The specific kind of table that I'm going to talk about today is not just a straightforward lookup table, but one that is adaptive, as you can see from the title. And also, it's a table that is not pre-processed and stored on your hard drive. Rather, it is generated in situ while the calculation is proceeding. This method was actually pioneered by Professor Steve Pope from Cornell University for computational combustion applications back in around 1997. So moving on, again, to get back to the original theme, there are numerous applications when it comes to large-scale scientific calculations where you may need one of these three types of calculations. For example, you may need a functional evaluation. I just gave the example where, let's say you have viscosity as a function of temperature. It's an equation, it's a function, right? So you may need to evaluate that. There are situations where within a larger calculation, you may have to essentially use a submodel where you need to solve one or multiple ODEs, ordinary differential equations. There may be other situations where you may need to solve one or many nonlinear algebraic equations. And I'll give you some more concrete examples. There may be even further beyond that, maybe other situations where you essentially combine the second and third bullet here to have a system of what's called differential algebraic equations. I come from the area of thermal and fluid sciences, and when we do reacting flow calculations, these are often encountered. People in the controls area also often encounter sets of ODEs or sets of differential algebraic equations. So here are some more concrete examples. I gave the example of, okay, let's say you want to compute viscosity. So for example, you do a reacting flow calculation. In it, you want to find the viscosity of the fluid, which is a mixture now, using some sort of, model. In this case, we are, let's say, using kinetic theory of gases. So what you would do is you would compute the viscosity of each of the individual species or components of the system, and then mix it up using this kind of a mixing law. It's a pretty complicated formula, as you can see. There are many, many floating point operations going on. So, computing this for each computational cell in your domain and for thousands of iterations means that actually you are doing many, many floating point operations. So one evaluation may have, for example, if you look at this formula, this may have 14, 15 floating point operations. So that times 10 million floating point operations. If you're doing 3D calculations, it may be even more. So there's a case to be made where you might say, well, instead of executing this formula again and again, I might store the data in a table and reuse it. Okay. You could also have, as I mentioned, a set of ordinary differential equations that you may want to solve. This is where Professor Pope actually came up with this idea, or this is the area for which he came up with the idea when he was doing chemical kinetics in the context of PDF methods for turbulent reacting flows. He realized that these calculations are very expensive. And so you might want to actually store the result and then just use it from a table. And similar situations are encountered for Eulerian reacting flow calculations as well. if you are doing, for example, surface reactions, again, same idea. This is a scenario where essentially this represents a nonlinear algebraic equations with n unknowns. Of course, there are n equations, so it's a system of n equations with n unknowns, but they're nonlinear equations. So you have to use a numerical method, like, for example, the Newton-Raphson method to solve the system, and that can be very, very expensive. So the fact that we are doing the same calculation within a larger calculation with minor change in the inputs. So for example, if I go back here, maybe the temperature changes a little bit from one cell to another, and you are having to recompute the viscosity. Similarly here, maybe the reaction rates change here slightly, and you're having to recompute, okay? And the reaction rate again may change because of slight change in temperature or concentration. Same thing here, the temperature and concentration represented by these variables P1 through Pn may change slightly, and you're having to recompute, okay? And so this makes the case for using a lookup table, okay? So it's a complex calculation, and therefore, instead of doing it again and again, which can be very expensive, you store the result in a lookup table and use it, okay? Now, we all are used to using lookup tables for a variety of applications. So you just have, let's say, y versus x. You want y at a given x, you interpolate within the table, and that's it, okay? Now, there are some problems to that. When you do it for a single variable, one input and one output, y being your output, x being your input, it's not such a big deal. But if you have multiple inputs and multiple outputs, you get a multidimensional table. Even if you have one output and multiple inputs, so let's say I have 5 inputs and one output, I have a 5-dimensional table, which means that even if you're putting 10 points in each dimension, so suppose your dimensions are temperature, pressure, concentration of species A, etc., you put 10 points in temperature space, 10 points in pressure space, and so on, you end up with, 10 to the power n entries, depending on what n is, how many inputs you have in the system. So that's a big problem because you end up with a very large table, even if you have a pretty coarse discretization in each direction. Second thing is you have no control over the interpolation errors. Your results are what they are. There's nothing much you can do about it because you are making an a priori decision on how to distribute these 10 points. Okay, they may be equally spaced, they may be non-equally spaced. Now, if they're not equally spaced, then you may have to do some numerical experimentation or some initial investigation to find out, well, where should I cluster the points to get a better answer? But it requires extra work, extra calculations. And then finally, if you have a multidimensional table, so if you, for example, have a 10-dimensional table and that many entries, just the search and retrieve from that table is probably going to be more expensive than doing the calculation directly. Okay, so this is the reason we cannot use these ordered lookup tables for the kind of applications I'm talking about. So this is where Professor Pope's idea came in situ adaptive tabulation. So what is the basic idea? So right off the back, I want to just say that I don't mean for this lecture to be a research lecture or research seminar. Rather, what I want to do here is to just explain the very basic concept with a very simple example to give you a flavor of how powerful it is so that you can use it for your own needs. Of course, for more complex problems, you have to read the detailed papers because there's a lot of math involved. So let's take an example. So suppose I want to solve this nonlinear equation. Okay, so the solution will give me x. For various values of a. So a is my input, which is, you may call it a parameter, and then x is your output or solution. Okay. So let's say we start off by saying that, okay, I choose a certain a, okay, which I call a naught, and for that the solution will be x naught. In other words, I solve this equation once. Okay. Then I say, if I now change this input a naught by a tiny amount, okay, or may not be tiny, by some amount, what will be the corresponding change in x? Okay, so the question is, this is kind of like interpolation within a table. You have x1 and x2, and I want a value somewhere between an x1 and x2. Okay. How much will the corresponding value of y change when I go from slight perturbation from x1? Okay. So that's the idea. If I change a little bit, how will the solution of x change? Okay. And that can be figured out very easily by just doing a Taylor series expansion. So here I have a 2D Taylor series expansion. So A0 plus delta A is basically the solution at a point where I'm deviating from the original point A0 by some amount delta A. And the corresponding root, obviously, to that equation that I showed on the previous slide will be x0 plus delta x. In other words, this is a change in the solution due to a certain change in the input. Okay. Now, of course, we are trying to solve this equation equal to 0. And this equation, this part here equal to 0 has already been solved. Okay, so we are going to strike those two out and set this remaining part equal to 0, which then gives us this equation. In other words, we are saying if we are given the change in A and we know the derivatives with respect to the input and as well as the derivatives with respect to the output, then we can figure out what the change in x will be, assuming that this linear approximation holds, because as you can see, there are higher order terms in the Taylor series that we have thrown out. All right. So that's the point. So this is kind of like a Newton iteration formula almost, but it's a linear approximation that gives us a change in x corresponding to a change in A. The accuracy of this approximation will obviously depend on how this function behaves, right? How the local derivatives are and so on. If it's a linear function, okay, then obviously this is an exact representation or an exact approximation. All right, so how does this algorithm work? So first I perform a direct calculation to initialize the table, okay? So again, bringing back our equation, this is the equation I'm trying to solve. And in this particular example, let's say we are going to change A, the input, between 0 and 1. Okay. So since it's going to change between 0 and 1, I'm going to initialize the table at the midpoint of that space that I'm working in, which is 0.5. Okay. So I create a point in the table, which is 0.5. Okay. So for A equal to 0.5, I solve this nonlinear equation directly. Okay, and once I solve it directly, I have the root, corresponding root, x0, and I can also calculate what the derivatives will be with respect to the input and the output at those values A0 and x0. Okay, and then finally, I have this quantity called ROA. What is this ROA? This is what we call the region of accuracy. This is a region around A0 where the linear approximation that we showed in the previous slide, that will yield an answer within a certain prescribed tolerance. Okay. In other words, we're saying that if I go slightly away from 0.5, let's say 0.51, and I use the linear approximation, it is going to give me an answer that is close to the exact root for A equal to 0.51 within a certain prescribed tolerance. Okay, that's what we are calling our region of accuracy. And initially, I'm going to set that region of accuracy for this point to be 0. Okay. So I have one point in the table. That's it. Okay. Now I come in with the next point. So I want to calculate now the root of this equation for a different value of A. And that different value, I'm going to call it AQ, the Q standing for query. In other words, we are going to call these new queries. Okay. So for a new query, AQ, I want to now find the root. So first thing I'm going to do is I'm going to check if this point is within the region of accuracy of A0. Okay, in other words, I'm asking this mathematical question, is the absolute value of AQ minus A0 less than the region of accuracy of A0? If the answer is yes, then we know that the linear approximation is a good approximation, and we are going to simply retrieve the value of x using this formula right here. Okay, so that's the idea. Now, obviously, for the first point, as I said, we have initialized the region of accuracy initially to 0, which means that the answer to this question will be no to begin with. Okay. So in this case, now we have two decisions to make, or rather one decision to make out of two choices. Okay. Either this new query AQ, we can make it a new entry in the table, or we can use it to actually expand the region of accuracy of the parent point, which is a equal to 0.5. Okay. Both of these, however, will require a direct calculation. In other words, we have to first solve the nonlinear equation to find the exact root xq for the query point AQ. Okay. So we have xq by solving the exact equation, the nonlinear equation. Next, what we will do is we will find the solution by using our linear approximation. So this is the linear approximation that I had 2 slides ago. I use that to calculate a new value of x, which I'm calling xc because it's an approximate value. It's not the exact value. And then what we will do is we will compare the exact value to the approximate value and see if it is within the prescribed tolerance. Okay. Now the prescribed tolerance is a number that you decide. So you might say, well, I want my answers within 10 to the power minus 4 or 10 to the power minus 3. That's the number that you decide. Okay. So if the answer is yes, if this is found to be within the prescribed tolerance, then what we do is we reset the region of accuracy of the parent. Remember, it was initialized to 0, but now we are resetting it to this new value. In other words, we're saying within this range, the linear approximation will be valid, and therefore I can grow the region of accuracy from 0 to a non-zero value. If the answer, however, is no, then you are going to add this point as a new entry in the table. You can add it now because you've already computed the exact solution. Okay, so just like we did for A0, we have also computed for AQ, so we can add that new point to the table. Okay, this first step is often referred to as the growth step, where we are growing the region of accuracy. Conversely, if the answer is no, then we add to the table, and obviously it's called an addition step. So for this particular example, the second point is 0.617. You might ask, how did you get that point? Well, I'm just drawing numbers for A randomly. So first I started with 0.5, then I drew a random number, which was 0.617. Okay, so that's how I got it. So for this case, the no criteria, if you do the calculation, you'll find that the no criteria is met. And so the point is added as a new entry in the table, which we are going to call child 1. Okay. In subsequent steps, what you do is you repeat these two steps that I outlined, step 1 and step 2, okay, or sorry, steps 2 and 3. You repeat them, but with the following generalization. So if child 1 already exists, then you perform the tests with child 1 first. And if the answer is yes, then you grow child 1. If no, then you add child 2. And if both children exist, then the no criteria, and if the no criteria is met for both, then add a new grandchild now to whichever child has lower region of accuracy, okay, or a lower value of AQ minus A0. Okay, so that's the general guideline. So if we again go by this specific example, this is the second random number that I drew. Again, what happened was the no criteria worked out in this case. And so this got added to as a new child, child number 2, to the parent, which is 0.5. Okay, so now I have 2 children. Okay, and then I'm going to draw the next point and make these decisions based on the algorithm and either add a new point or grow an existing point and so on. So I'm just going to show you what happens when you execute the full algorithm. So I start with point 1, and I'm going to call it my 0th point because this is just initialization of the table. It's an addition step, right? Then I get the next one, which is an addition step also. These three you've already seen. Addition step, then I get to the next one, which after doing all the checks ends up being added as a grandchild essentially to this guy here. Okay, so that's another addition step. Then I get 0.77, which also gets added. 0.17, which gets added to this branch instead of this branch, because one of the checks, remember we said whichever one is closer to, that's the one it gets added to, and so on. And it keeps propagating like that. Okay. Now, when you hit this 8th point, something interesting happens. You suddenly find that the growth criteria is satisfied, and actually this point ends up expanding the region of accuracy. So up to this point, all of these points have zero region of accuracy. Zero region of accuracy means you cannot retrieve any values from the table, because whatever value you pick, it is not within the region of accuracy of any of the points in the table, and so you cannot retrieve anything. Okay, you have to grow these points before you can retrieve. But fortunately, it turns out that by the time you get to the 8th point, you get growth. Okay. Again, next point gets added. Next point, again, you end up with growth. Next point gets added. Another point gets added. Now you get growth. Another point gets added. So you see this table is growing deeper and deeper layer-wise. Okay. And then 16 is again growth. All right. And finally, the 17th point is where we find that we can actually retrieve from this region of accuracy. Now, you might say, well, 0.7, how is that between 0.8 and 0.6? Well, you have to understand that it's a deviation on both ends. So it's, if you think about this as 0.02 deviation, it's 0.58 plus minus 0.02 in a sense. Okay. So that's why this ends up being the region of accuracy. But of course, we do the actual math to see that it indeed works out. And so we retrieve. Okay. So this is exactly how the table works. You start off with addition to the table mostly initially, then there's a lot of growth. And then towards the tail end, you start retrieving values. Now imagine you were doing this calculation in the context of a larger calculation. What would happen is you would start creating the table, and after some point you would find that you are not having to create data in the table anymore. You are simply retrieving data, which is going to be hopefully very, very fast. Now bear in mind that there is a cost to actually traversing this tree, this binary tree, in the sense that you still have to do search and retrieve. Okay, it's not completely free. In other words, there are overheads even if you're doing a direct retrieval like that. Okay, but it is hopefully not as expensive as a direct calculation. So that being said, if we look at the full performance, so just some general comments first. So if there are key points in the table, let's say just making up some number 10 to the power 4 and Q queries, and I'm making these numbers large. Okay, many queries. Conventional lookup table, and this is, I'm talking about a one-dimensional table now, you would have to search at least half the table. Okay, so for each query, you would search half the table, and that would give you that many searches. Okay. Now, if you use this sort of a binary table that I am showing you here, okay. Now, for one dimensions, you can also think of this sort of like executing a binary search algorithm, but the basic idea is the same. Here, what ends up happening is that you actually end up doing logarithm base 2 of that, which ends up being substantially smaller, as you can see, 2 orders of magnitude smaller number of searches. So this is one of the advantages of using binary trees as opposed to ordered lookup trees. The search is a lot more efficient. Okay. All right, so for the specific example that I considered here, so the direct calculations I just want to mention were done with the Newton-Raphson method with an under relaxation factor of 0.5, and I simply use that because sometimes the Newton-Raphson method doesn't want to converge if you use an under relaxation of 1 exactly. So just to be safe, because we are doing so many calculations, I used an under relaxation factor, and I set the residual to 10 to the minus 9. In other words, your function will be 10 to the minus 9 or less, absolute value of the function. And then the prescribed tolerance for retrieval is 10 to the minus 4. So any answer for x that is within 10 to the power minus 4 will be accepted. Okay, otherwise it will be rejected. So here is a summary of what I found when I executed these calculations. What I found is that you only needed 53 entries in the table. Okay, these are the number of points that I'm doing calculation for, but only 53 of those ended up creating the table. Then a huge number got retrieved from the table, and if you take 53 plus this 588, so that's about 640 something. Okay, so about 350 or so values actually are of these A values contributed to the growth. Okay, so this is what got retrieved, about 350 contributed to growth, and these are the actual number of entries in the table. Okay, CPU time wise, when I used this in situ tabulation, it took me 8.9 seconds to do that many calculations of that nonlinear equation within a prescribed tolerance of that. Okay, if I do direct calculations, I found that it actually takes me 179 seconds. So you can see this is approximately a factor of 20 speed up. Okay, now this is a very simple problem where the direct calculation is not as expensive. The method actually gives you much higher returns if the direct calculation is really expensive. And if you have multiple inputs and outputs, multidimensional problem in a sense. So keep that in mind. But this was just to give you sort of the tip of the iceberg, just a basic idea of how the algorithm works. Hopefully you appreciate its power and can use it later on. Just to look at the accuracy, you can see these are the different values of A that were input. I've just taken some random query numbers, and these are the A numbers that were used, and correspondingly these are the retrieved values of X, okay, versus the X calculated using a direct calculation, okay, and the difference is of course the error, and as expected all of them are below 10 to the power minus 4. Okay. Now, how do you extend all this to multidimensional problems? Let's say a system of nonlinear equations. That is where things get quite complicated. Instead of using a simple formula like this one here, you are now going to have, you can see here, there's a scalar derivative here. Instead of those, you're now going to have a Jacobian of partial derivatives, which finally end up giving you this. So this is the Jacobian with respect to the outputs. This is the Jacobian with respect to the inputs. And you have to, do matrix inversion, store these Jacobians. So there's a lot of storage involved. There's a lot of calculations involved. And then your region of accuracy is now going to become what's called a hyperellipsoid of accuracy. And to actually compute that hyperellipsoid of accuracy, you will have to do a singular value decomposition, which again can be fairly expensive. So all these details are spelled out in Professor Pope's papers and then papers that came afterwards, including some of my papers. The tolerance, of course, in this case is also a vector, and you can set it independently. It doesn't have to be one value for all the unknowns. And generally, because the storage now becomes high, at each point you are storing a matrix rather than single values. You have to kind of place a cap on the number of entries in the table. Okay, so these are just some things to watch out for when you get to multi-dimensions. So in conclusion, and again, as I said, I'm not going to go over the details for multidimensional problems. You can look it up yourself. I'll show you some references in the next slide. But some conclusions, it's a procedure, ISAT is a procedure that replaces conventional lookup tables. It's a binary table, number one. Number two, it's created in situ while the calculations are going on. You don't have to create and store it a priori. It should really be used if the direct calculation is expensive, because If it is not expensive enough, then the cost of search and retrieval from the table will actually supersede the cost for the direct calculation. And then, of course, the algorithm is not going to pay off. Binary table, I mentioned already, it facilitates search. The method creates the table in situ. We talked about this. Error of creation and retrieval can be dynamically controlled. This is a big advantage. You just saw that. You are actually prescribing the tolerance rather than saying, okay, I create 10 points in the table and when I do interpolation, whatever the error, that's what I have to live with. No, it's not like that. You're actually controlling the error. For multidimensional problems, you need large RAM because the table is stored in your memory, not on the hard drive. Okay. Now, of course, even for lookup tables, you may store it on your hard drive, but you have to read in the lookup table before using it if you're using it in a computer in a large-scale calculation. Okay, so that's not such a big issue, but that's something to keep in mind. Some people actually can write out the ISAT table at the end of their calculation so that they can reuse it later. And the big trade-off is between efficiency and memory. So the larger the table, the more memory you will require, but that will also give you higher retrieval percentages or higher efficiency. Okay. Here are some references. This is the original reference of the paper that I mentioned by Professor Prof. The method has been used extensively since then, not only for computational combustion applications, where of course there are many, many papers on ISAT, but even other areas. So this is a paper where it has, for example, been used in control engineering. And here's a paper by one of my graduate students that uses it for surface chemistry rather than gas phase homogeneous chemistry, for which the original paper was developed. So with that, I will stop. Hopefully you've gained something useful from this lecture and are able to follow up and use this method if so desired. Thank you.